Hello and welcome to the Migration Mapper demo series. My name is Jerod Merkle and I'm an assistant professor at the University of Wyoming and a research associate with the Wyoming Migration Initiative. This video, I'm going to explain to you a bit about App 4 or Module 4, where we're actually taking our sequences and our point data and turning it into both utilization distributions or occurrence distributions and footprints of use, which I will explain a bit more now. So before we jump into the app, I just want to explain that in kind of a more detailed sense. So we've basically in app 3 have identified these snippets of raw point data. And what this app is going to do is going to provide us two things, this app 4. And that is it's going to basically take those points, put them in sequential order, and then do a number of different things to it, or there are options that you can decide to do. The first is create an occurrence distribution, which is basically a probability distribution or a heat map of where the animal spent time. And there's a number of different movement model methods to do this, and we'll have options to do that. You can also take this line and then just buffer it, and that will give you kind of a footprint of use. And you can also take this heat map of use and take a contour of it and create what we call a footprint. And so the outputs from this fourth app are going to be basically occurrence distributions, so heat maps for each one of these little sequences, and a footprint of use from each one of those sequences. And so that's where this app is going to do for us. So that's a little bit of conceptualization. Now we can jump into the app itself. This is what it looks like. There's tons of buttons and options here to think about. And the first thing in the upper hand left corner is basically a summary of the different methods that we can do within this app. So we have the regular Brownian bridge movement model. This is a method that we typically do for mapping migrations. This creates one single, what we call Brownian motion variance, which kind of is an index of kind of how far an animal goes between points, or how messy or how tortuous their movement is between points. And with that method, we also have an option to fix that. Either it estimates that motion variance itself, or you can fix it yourself so all the animals have the same exact one. That gives them kind of the same amount of error associated between any 2 points. We also have the dynamic Brownian bridge movement model. This one actually allows that Brownian motion variance to vary as time goes on during the movement of that animal. And so if it's more, kind of on a stopover and making circles, it'll get one Brownian motion variance, but then if it's more directed movement, it'll get a different Brownian motion variance. So those are the main two functions, those two related to Brownian bridge movement model. Then you can also just do a kernel utilization distribution, the really basic bivariate normal kernel distribution. This one also gives you an option to subsample data beforehand. So a lot of folks that want just kind of the general area of use, they don't want the actual movement areas, may want to do a kernel UD and subsample the data to 1 point a day, for instance. So all the animals have the same amount of data per day, and then you can create a kernel utilization distribution. We also implement some of the continuous time movement model options from the package CTMM. These calculate occurrence distributions. There's a bunch of different nuance to it, but it typically is a little tighter than the Brownian bridge movement model or the dynamic Brownian bridge, definitely tighter than the kernel. But it also can be a little bit finicky, and sometimes those models don't fit as well. But it gives you another option. These are probably best if you have really sparse data or collars that have a kind of a real mix of different fixed rates, because this model is it helps you with that. And then the final thing is the line buffer method, which basically, as you can imagine, connects the dots with a line and then gives it a user specified buffer or a radius around those lines. And so you can very quickly identify footprints of use. So note that this method does not give you any kind of occurrence distribution or heat map of where the animal goes, only footprints. But the other 4 methods give you both. I like to do the line buffer really quickly to just because it fits really fast and you can get a quick idea of where your animals go with the line buffer. But once you get down to it, you may want to actually do a Brownian bridge model, etc. Okay, those are your options. Now you have configuration parameters, and every section here tells you which methodology it pertains to. So if you're going to do the Brownian bridge method, you want to just look for the Brownian bridge in here. So this is like the contour level that you're going to grab. This is some parallel processing information. These are some buffers. So you have your data, and it applies some buffers to the population grid. So it adds, this is saying adds 30% to the grid for your entire population grid of how these methods are created. Then within that grid, what is the cell size? So you can be up to 500 for the cell size, or no, you can go anywhere from 20 meter resolution up to thousands meter resolution. My suggestion to you is start with something like 500 or 1,000 meter resolution, get things working properly so you understand how they're working. Then if you want to get more precision, then crank it down to 50 or 100 meter resolution. If you're doing the line buffer, this is the radius for the line buffer. If you are going to force the motion variance for regular Brownian bridge, this is where you would type it in. If you leave it blank, it will estimate the Brownian motion variance for each one of your sequences separately. This is the location error for your GPS collar data. This is for the dynamic Brownian bridge and regular Brownian bridge. This is your max lag for the Brownian bridge and dynamic Brownian bridge. This is very key here. And what this value gives is if you have 2 points in your data that are more than 8 hours apart, it will not create a bridge between those. It will not connect those 2 dots and estimate a Brownian bridge movement model between them. And the thing is that you want to be careful here is it's good to have this as kind of a low value, because what happens is the farther or the more time between points, the animal could have gone anywhere. And so you want to be careful with this value. If it goes up to 12 or 24 hours breaks in data, there'll be a big blob of where the animal could have been between those 2 points. However, let's say you put 8-hour data into the migration mapper and then you left this value at 8 hours. Every time your collar missed a fix, it will not connect 2 points. And it can cause problems with the fitting of the Brownian bridge movement models. So you need to be very careful with this max lag. Typically, if you have like 2-hour data, 3-hour data, 1-hour data, a max lag of about 8 is a really good estimate. So it allows your collar to miss a point, miss a fix. So if it was 3-hour data, it would be suddenly 6 hours between points, and that would be below this threshold of 8. And so it'll still connect those 2 points and make a Brownian bridge between them. Okay. Then we have the time step. This is really focused on how the Brownian bridge movement model is integrated. You can read about that if you want. There's a max timeout. If some of these models are running for a long time, it'll actually just stop them in case it doesn't fix. It helps you with error management, and it should tell you there was a max timeout. If you're getting that a bunch, but you think the data are okay, you could increase this to more than 12 hours. These next 2 are for the dynamic Brownian bridge movement model. This is the margin and the window. These are used for that moving window analysis to estimate the Brownian bridge motion variance as the animal moves along. You can see more details in the Brownian bridge.dynamic function there. If you do the kernel UD, here's your smoothing parameter. If you leave it blank, it'll give you that href method, which is the default. If you actually give it the value, it'll force that smoothing parameter as the value. If you want to subsample your data using the kernel method, You just give it a numeric value, and it will be taken as the number of random locations to sample per Julian day per year for that individual. And then the final thing is for the continuous time movement models, it's a model selection criteria for figuring out which movement model to apply to your data before estimating that occurrence distribution. And you can read more about that in the CTMM package. Okay, so let's just start with a regular Brownian bridge. I have 500 meter cell size, and let's just do, you can either do all of them together or you can do them one at a time here. Let's do migration spring. Hopefully this doesn't take too long. If it does, I'll pause the video. But what this is doing is it's looping through each of your individual or each of those sequences that were created in the previous app and calculating the Brownian bridge movement model and doing the footprint. So it's getting the occurrence distribution and the footprint. So this looks successful. I'm going to zoom out a little bit. And so what you get here is a little table that tells you here are all the sequences. So this is animal ID 1, biological year 2011, and this is migration spring. This was the estimated Brownian bridge motion variance. This was the size of the grid that was needed for this individual. That's the cell size. This is the date it was created. This will be character in your output, how long it took, how many relocations were there, the start date, end date, et cetera, et cetera. You can also find this information if you go back to your project folder. You will now have footprints, UDs, metadata. So if you go into here, you'll have this metadata. If you open this, this is exactly the same information that we saw in there. So this will have the start and end date for every single one of these sequences. They were all successful. I don't see any errors. And in the metadata folder, there's also some distance information. So this is the max distance in kilometers that the animal moved, the mean maximum distance across all the individuals, et cetera, et cetera. So just a bit of information there. And let's look in the footprints. So now in the footprints folder, there's migration spring. And this is the footprint for each of the animals or each of the sequences. This is the UDs or the occurrence distributions for each animal. You can see a little bit in these folders. And so everything has been put in there. And we could also do, I did migration spring. Let's do migration fall now. So that'll run that one in the same situation. And by the way, anytime you finish one of these, you can always jump over to app 6 and have a look at what you did. And then you could come back to app 4 and maybe change it if you want it. So here are the fall migrations. Doesn't look like there's any errors. I can go in here. Again, I can go into the metadata. So the fall, no errors, etc. Can look at that. And you'll see now in the UDs, now we have both fall and spring, and we have all those files. These are all raster files of the footprints and the UDs. So let's leave that. I'm going to leave the other two. I'm going to jump to app 6 so we can have a look at what we've done. Oh, maybe it's not working. Oh, there we go. So if we go to app 6 and reload it, basically what it's going to give us is all of our lines. So it's not actually going to show us our footprints because those are rasters, but we have our migration lines for fall, migration lines for spring. You can see them showing up over here. And then we have, let's put the summer core points on there, or we can do winter date points. So that gives us the main winter areas, or the lines for winter, et cetera, et cetera. So this is pretty nice to be able to see this in your data. Okay, that settles it for app 4. Thanks a lot, and we'll see you later.